Hi everyone, my name is Chen Jordan, with Jordan being my first name. Here, I'm presenting our work, Efficient Attention. One of the main motivations behind our work is that long-range interaction modeling is important to deep learning. However, traditional architectures struggle at solving it. The solution proposed to this problem is dot product attention, which computes a query, a key, and a value at each pixel, and then pairwise matches queries to keys to form the attention scores, and then uses the attention scores to aggregate the values. This mechanism effectively establishes long-range interactions in one shot, because it densely connects every pair of pixels. However, that also means the complexity for memory and computation is order n squared for this module. This would translate to gigabytes or even terabytes of memory per example on high-resolution images or videos. Seeing this challenge, we propose efficient attention, which is a linearly complex attention module with the same representational power as dot product attention. Our core observation is that in dot product attention, there are two consecutive matrix multiplications. Therefore, we can utilize the associativity of matrix multiplication to switch the order of computation and massively reduce the size of the intermediate output and therefore reduce the complexity from quadratic to linear. The final missing piece is that we have to split the single normalization function to two normalizers, one on queries and one on keys. If you have a nonlinear normalizer on the original dot product attention module, then this operation would break the mathematical equivalence between dot product attention and efficient attention. However, we have empirical results to show that this approximate equivalence does not impact performance at all. With that, we have obtained the efficient attention module, which is an attention module that can establish long-range interactions in one shot in linear space and time. Now, the next question is that, how does this theoretically beautiful module perform in practice? We tested our module on 3 different datasets for 4 different tasks. Our main dataset is MS COCO 2017. We first validated our hypothesis that the approximate equivalence between efficient attention and dot product attention does not impact performance. For that, we test our module against the local module, which is a concrete instantiation of dot product attention. As you can see, when we insert either module into different layers of a network, they almost always give identical performance. However, at layers where the input size is large, then a local module would require huge amounts of memory, which results in out-of-memory errors. Therefore, efficient attention has a much higher performance ceiling given the same resource constraints. We also compared our methods against other recent efficient and local methods. As you can see in this table, our method achieves the largest performance gain using the least amount of resources. To test the effectiveness of our module on video data, we tried temporal action localization on Thumos 14. As you can see, we consistently beat the RC3D baseline across all IOU thresholds. We also tested on stable depth estimation, which is a task that operates on 2.5D data. As you can see, on the SyncFlow dataset, we beat both our baseline and other state-of-the-art approaches. For future directions, we believe efficient attention has a wide array of applications as a drop-in replacement for dot product attention. Specifically, it can serve as the building block for efficient visual transformers or efficient transformers in general. With that, thank you for watching my presentation today, and see you in our Q&A session.